Dr. Jones, noticing that the traitorous pilots have leapt out of the plane, taking all the spare parachutes with them, he himself jumps out the plane with only an inflatable raft. Rides the raft down, crashes onto the snowy slope, rides down the slope towards this cliff, and launches out over this river. Meanwhile, the plane, pilotless, crashes into a nearby mountainside. From this moment on, once he leaves the snow, we have a projectile problem. He is no longer in contact with the surface and will ignore all air drag on the raft. So, once it's a projectile, we know it's going to move on a parabolic path. Let's dot in what his path might look like once he leaves the cliff out over the water and hopefully splash down somewhere over here. We got a couple of questions to answer. How far from the base of the cliff will Dr. Jones land? We'll call that our distance delta x, changing the x coordinate from his current position to where he lands. And at what angle does he hit the water? The moment he hits the water here, we can draw in his velocity. We know it'll be tangent to the path, so he'll be hitting the water with a velocity something like that. And we want to know what is the speed when he hits the water. Okay, so as always with projectile problems, we have to identify two events at a time to consider. Event 1 will be the moment he leaves contact, launches horizontally from the cliff, and moment 2 will be when he hits the water right there. Now we can start identifying some more variables. This here is his initial velocity at moment 1, and then this will be his velocity at moment 2. We want to know the angle at which he hits the water. It would be convenient to find this angle right there, because this here, this leg of the triangle, would be v2y, the y component of velocity 2, and the component here is just going to be vx. I don't have to say vx2 because we know that the x component of velocity will be constant throughout the entire time he's in free fall. Okay, so we've identified our moments, some variables. Now we go back to the trusty guess procedure for setting up our information. Sort of setting up what we know, deciding how we're going to proceed, and then proceeding. So starting with our givens and unknowns. Our projectile equations here have the following variables in them. These are the variables we're going to be looking for to decide which are our givens and which are our unknowns, the horizontal part and the vertical part, and remember that time is the bridge between the two. Okay, in this problem, for our givens, we know that, let's see, the change in y between those two moments, well, he drops 130 meters, but he ends up lower than where he started. His change in y was downward, was negative, so delta y is a negative 130 meters. Let's see. Oh, we also know his launch velocity. I forgot to tell you that. Let's say his launch speed here is going to be 4 meters per second. Okay, about close to 8-10 miles per hour. Not so fast when he launches off this ridiculously high cliff. Okay, so we know that Vx is going to be 4 meters per second because this is a horizontal launch. The initial y component of the velocity is 0. It's only moving in the x direction. So if the magnitude is 4 meters per second, that's all the x direction. So Vx is 4 meters per second. And then Vy1 is, I should call it V1, y, the initial velocity y component, that is 0. That's a key piece of information, that you're not moving in the vertical direction at the moment of launch. V1y is 0. Okay, I think that's about all we know here. Let's write down some unknowns. Obviously we don't know delta x. We don't know his y component of velocity when he hits the ground. We don't know v2 2y, and we don't know how long it's going to take him, how long he's going to be in the air. Okay, with that information, let's try and tackle question 1. How far from the base of the cliff does he land? Let's see if we can find delta x. We'll look at our equations and check each of them, determine which information you know and which you don't. So in this equation here, I don't know delta x, I don't know time, but I do know vx. That's two unknowns, can't use that one. Over here, I don't know the change in y because I change in the y component of the velocity because I don't know his final y component of the velocity, or the y component of his final velocity. So I don't know that, and I don't know time. Oh, that's no good. This one here, I do know delta y. I do know that v1y is 0. That whole term drops out. And then I don't know delta t, but that's only one unknown. I can solve this one. Let's keep looking. I don't know the second, the y component of the second velocity, but I do know delta y. Aha, so I could solve this one too. If we want to get over to figure out delta x, we need to know the time. We have to solve for the time over here and bring the time over, and then we can solve for delta x. So this equation right here, I can solve for the time right now. So that's the one we want. So next step is to write down the equation that you're going to use. Delta y equals v1y delta t minus 1/2, and then remember that we use the letter little g to represent an acceleration of 9.8 meters per second squared. That is 1g, the acceleration of an object in free fall. So I'm going to use the letter g to represent 9.8 meters per second squared instead of writing this out over and over again. But I am going to write that negative sign there explicitly. So negative 1/2 g is 9.8 meters per second squared, and then delta t squared. We know that v1y is 0. So our next step is to solve algebraically for the variable that we want to know. We want to get delta t here. So I can multiply both sides by 2, divide both sides by g, multiply both sides by that negative 1, and then take the square root of both sides to find that delta t equals negative 2 delta y all over g. I'll take the square root of that whole thing. Now it's time to substitute in the numerical values. It's useful to find this expression in terms of variables first, but now we can put in our numbers. So delta t equals negative 2. Negative may be worrisome because you can't take the square root of a negative, but remember that delta y is itself negative 130 meters. So negative 2 times negative 130 meters all over, and g is defined to be a positive 9.8 meters per second squared. Square root of that whole thing, oops, that gives us 5.15 seconds. Okay, we can take that part over to the x side. We need a new equation here, so we'll kind of start this process again. The other equation we need is that delta x equals vx delta t. We've already solved for, it's already arranged to solve for delta x, so now we just substitute in our values. Delta x is our initial, vx is 4 meters per second, and delta t 5.15 seconds. So that comes out to 20.6 meters. There we go. That's how far he lands from the base of the cliff. Okay. Part 2. Part 2 is to find the angle. Looking back at our equations, to find the angle, we will need to know the y component of the final velocity. And we can get that from this equation here. So the equation that we're going to be using is delta vy squared equals negative 2g delta y. It's negative 2g delta y because there's a negative, there's a 2, and g is just the positive 9.8 meters per second squared here. All right, let's rearrange that. Let's see. So this is Vy2 squared minus Vy1 squared. That's what this left-hand side means. Equals negative 2g delta y. Vy1 is 0. So to rearrange to solve for what we want, Vy2, just take the square root of both sides, is negative 2g delta y square root of that whole thing. So Vy2 is negative 2, g is 9.8 meters per second squared. This is our substitute step where we're putting the values in, and delta y is the negative 130 meters. That way our negative becomes positive. Square root of all of that gives us, I forgot. 50.5 meters per second. And we know he's going down at that point, so we have to throw on a negative. The y component is negative 50.5 meters per second. Okay, so if we draw in our, well, let's look back at the picture. We now know this is negative 50.5 meters per second. We know Vx has stayed constant. That's still 4 meters per second. So tangent of theta is Vx over V2y. Tangent of theta is Vx over V2y. I said Vy2 here, but it means the same thing. I should have written V2y. Okay, so then theta is arctan of Vx over V2y, which is going to come out to, well, let's put the numbers in, arctan of 4 meters per second all over 50.5 meters per second. The negative sign doesn't matter when I'm finding the angle here. That's going to come out to, oh, I forgot, 4.9 degrees? No, 4.5 degrees. Comes out to 4.5 degrees. Pretty steep. So then the speed with which he hits the ground is going to be V2y squared plus Vx squared. Use Pythagorean theorem on that final triangle. So that's the negative 50.5 there, and that's the 4 there. That's going to come out to about 50.6 meters per second. He's going to hit the water a little over 100 miles per hour, coming more or less straight down. That's a tiny 4.5 degree angle there, so he's coming more or less straight down, hitting the water at 100 miles per hour. That doesn't sound too good for our hero. Fortunately, we had to ignore the air drag that's going to save him. In reality, there'd be air drag on him. But we treated him like a projectile, so he's going to be hitting the water pretty hard.